Standing over 300 feet long, reaching higher than a 30-story building, a single wind turbine blade is one of the largest one-piece structures ever engineered by man. These are not merely fans, they are aerodynamic masterpieces designed to capture the invisible force of the wind and convert it into gigawatts of clean energy. But creating a structure this large and this light presents a massive engineering paradox. It must be flexible enough to withstand hurricane-force winds, yet rigid enough to never strike its own tower. Every millimeter of its curvature is calculated to maximize lift, much like the wing of a jumbo jet, but on a scale the aviation world can only dream of. In this deep dive, we are going inside the secretive world of composite manufacturing to see how sand, glass, and resin are transformed into a carbon fiber titan. This is the story of how we cast the giants of the sky, from the first layer of fiber to the final high-gloss finish. We start at the very beginning, where chemistry meets structural engineering. To build something this big, you can't use steel. It would be far too heavy for the wind to turn. Instead, engineers turn to the world of advanced composites. The blade is a sandwich of three primary materials: fiberglass, carbon fiber, and a surprisingly natural core, balsa wood. The fiberglass provides the bulk and shape, while strips of high-modulus carbon fiber act as the spine of the blade, giving it incredible longitudinal strength. Thousands of rolls of glass fabric are delivered to the factory, each with a specific weave pattern. Some are unidirectional, designed to handle tension, while others are biaxial, meant to resist twisting forces. The balsa wood, sourced from sustainable forests, is cut into hexagonal blocks and sandwiched between the layers. This creates a honeycomb effect, providing thickness and stiffness without adding significant weight. This material science is the foundation, but the real magic happens in the mold, a massive, heated cradle that spans the length of a football field. Every single layer must be placed by hand with sub-millimeter precision, because even a small wrinkle could lead to a catastrophic failure in the field. The manufacturing process begins with the mold, a two-piece clamshell structure that is a marvel of engineering in itself. These molds are crafted from reinforced composites and are equipped with internal heating elements to control the curing process. Before a single fiber is laid, the mold is polished to a mirror finish and coated with a specialized release agent. This ensures the blade doesn't bond to the mold during the heating phase. The precision here is absolute. If the mold is off by even a fraction of a degree in its curvature, the entire blade's aerodynamics will be compromised. The factory floor is a climate-controlled environment, where humidity and temperature are kept constant to prevent the materials from expanding or contracting. Laser projection systems overhead beam glowing green lines onto the mold surface, guiding the technicians as they begin the layup process. It is a slow, rhythmic dance of human labor and laser-guided accuracy as hundreds of layers of fabric are meticulously stacked. The stakes are high. A single stray hair or a speck of dust could create a weak point in the composite matrix. At the center of the blade lies the spar cap, the structural backbone that carries the majority of the mechanical load. For the largest blades, those exceeding 100 meters, this backbone is made primarily of carbon fiber pultrusions. Carbon fiber is 5 times stronger than steel, but significantly lighter, allowing the blade to grow longer without becoming too heavy to spin. These pultruded planks are pre-cured and then embedded into the fiberglass layers. This creates a concentrated zone of immense strength that runs from the root of the blade, where it attaches to the hub, all the way to the tip. As the blade rotates, it experiences massive centrifugal forces and bending moments. The spar cap must absorb these forces, flexing slightly like a fishing rod without snapping. The integration of the carbon spar and the fiberglass skin is the most critical bonding step in the entire assembly. Engineers use a step tapering technique, slowly reducing the thickness of the spar toward the tip, ensuring a smooth transition of stress throughout the 60-ton structure. It is a delicate balance of mass and muscle. Once the dry fibers and balsa core are perfectly positioned, the entire mold is sealed under a massive plastic vacuum bag. This is the moment of truth, the resin infusion. Using powerful vacuum pumps, all the air is sucked out from the mold, creating a powerful negative pressure. Then, valves are opened, allowing liquid epoxy resin to be pulled into the vacuum. This isn't just pouring, it is a controlled chemical flood. The resin must penetrate every single layer of fiber, saturating the glass and carbon to create a solid, monolithic structure. This process, known as vacuum-assisted resin transfer molding, is remarkably efficient. It ensures there are zero air bubbles or voids inside the laminate. Air bubbles are the enemy of composites. They act as starting points for cracks. The resin flow is monitored by thermal cameras and flow sensors, ensuring the liquid reaches the tip and the root at exactly the right time. The chemical reaction is exothermic, meaning it generates its own heat as it begins to harden. The blade is literally coming to life through a controlled fire of chemical bonding. Now that the resin has saturated the fibers, it must be cured to reach its full strength. The mold's internal heating system scales up, bringing the temperature to approximately 80 degrees Celsius or 176 degrees Fahrenheit. This temperature must be maintained with surgical precision for several hours. If the heat rises too quickly, the resin could become brittle or the blade could warp. If it stays too cool, the chemical bond won't fully cross-link, leaving the blade soft. This baking process transforms the liquid resin and soft fabric into a rigid, stone-hard composite. As the molecular chains lock together, the blade achieves its final structural integrity. Technicians monitor the TG, or glass transition temperature, ensuring the material has reached the desired state of molecular stability. Once the cure is complete, the cooling process must be just as controlled. A rapid drop in temperature could cause thermal shock, leading to microfractures deep within the laminate. It is a slow, agonizing wait as the world's largest single-piece structure solidifies in the dark. While the main body is often cast as one piece, many manufacturers use a two-part construction that must be fused together. Two separate molds, the pressure side and the suction side, are prepared. To join them, a specialized structural adhesive is applied to the internal webs and the leading and trailing edges. This adhesive is a high-strength epoxy paste designed to be even stronger than the blade material itself. Massive overhead cranes then lift the top mold, flipping it over with incredible grace and lowering it onto the bottom half. This is the master join. The alignment must be perfect, down to the millimeter. Once closed, the adhesive is cured, effectively welding the two halves into a single hollow shell. Inside, vertical shear webs connect the top and bottom spar caps, forming an I-beam structure that prevents the blade from collapsing under its own weight. This hollow design is what makes the blade so remarkably light for its size. It is a masterclass in structural efficiency, maximizing strength while minimizing every unnecessary gram of mass. The most stressed part of the entire blade is the root, the circular end that connects to the turbine's hub. Here, the blade must transition from an aerodynamic airfoil to a perfect circle. But there's a problem. How do you bolt a plastic and glass blade to a steel hub? The answer lies in the root inserts. Dozens of massive, high-tension steel bolts are embedded directly into the composite laminate during the casting process. These bolts are the only things holding the 60-ton blade against the centrifugal force of rotation. A specialized CNC milling machine then grinds the root face to a perfectly flat surface, ensuring a flush fit against the pitch bearing. The precision here is vital. If the root isn't perfectly flat, the bolts will experience uneven loading, leading to metal fatigue and potential failure. Each bolt is tightened to thousands of foot-pounds of torque. It is the ultimate bridge between the organic, curving world of composites and the rigid, uncompromising world of heavy steel engineering. This is where the wind's kinetic energy is finally transferred into the mechanical drivetrain. Before a new blade design is ever allowed to catch the wind, it must survive a trial by fire. In massive testing facilities, a prototype blade is subjected to the torture test. Huge hydraulic rams pull and push the blade, simulating 20 years of wind gusts in just a few months. This is fatigue testing. But the most spectacular test is the static load test. Cables pull the tip of the blade until it bends at an impossible angle, often more than 30 feet from its neutral position. The sound is terrifying, the groaning and popping of glass fibers under immense tension. Engineers use acoustic sensors to listen for internal delamination, the sound of layers peeling apart. They also use lightning strike simulation, zapping the blade with millions of volts to ensure the integrated copper grounding system can safely spirit the electricity into the ground. Only when the blade survives these extreme loads, without cracking or failing, is the design certified for mass production. It is a brutal, necessary validation of the 1,000 man-hours that went into its creation. The final stage is all about protection. In the open ocean or high plains, a blade is bombarded by rain, salt, sand, and insects. At the tip, the blade can be moving at over 200 miles per hour. At those speeds, even a raindrop can act like a bullet, eroding the leading edge over time. To prevent this, the blade is coated in a high-durability, UV-resistant polyurethane paint. A specialized leading-edge protection tape or coating is applied to the front, creating a sacrificial layer that can be replaced every 10 years. Finally, the blade is balanced. Small weights are added internally to ensure the center of gravity is exactly where it needs to be. When 3 of these blades are joined at the hub, they must be perfectly matched, like the hands of a fine Swiss watch. As the blade leaves the factory, it represents the pinnacle of modern manufacturing. A 100-meter-long, single-piece marvel, born of sand and resin, ready to harvest the breath of the planet for decades to come. Engineering has turned the invisible wind into the visible power of the future. I hope this deep dive gave you a new perspective on the strategies and the relentless mindset behind these global icons. If you enjoy deconstructing business empires and tech legends in this tech archive style, make sure to hit that subscribe button and turn on all notifications. That way, you will never miss a new blueprint of history. For those of you ready to explore more boardroom coups and technological breakthroughs, I have handpicked 2 videos for you right here on the screen. Click one to keep watching. I will see you in the next one. Thanks for watching.